Good afternoon. My name is Mitch Robertson. I'm the Director of Enterprise Systems for Curo Financial. Welcome back to my channel. Thank you for coming out. I hope you get something out of this. This is something pretty cool that I've been thinking about for a long time. I actually tried getting this going a while back and didn't quite take off, but I've decided to just start putting this stuff out because I think it's something that's lacking. And so this is the second in the series based on an interview question. We're going to talk about the TCP three-way handshake. This is really based on an interview question of what happens when I type www.google.com in my browser. The thing about this is I think it's extremely important to understand because this is the basis of pretty much all connectivity for all devices around the internet, even in the data center. There are a few things that connect over UDP and have a little bit different function, and I actually probably will do a series on that as well. But this is pretty much the way things connect for the most part. If you're sending an SMTP message, it's going to go through the same name resolution, TCP three-way handshake, TLS handshake, if we're going to encrypt it and hide the data, HTTP request, or it could be an FTP request, or it could be an SMTP request or response. And then we generally close out the conversation. There's a lot of different things that take place during this process, and there's a lot of value in understanding how things connect and how things talk. So again, this is the second in the series, and really wanting to get into talking about how this actually works, right? And how that three-way handshake works, and kind of the importance of understanding the data that you can get out of that three-way handshake. So we're going to get started. This is the TCP three-way handshake. And so right out of the chute, there's some really nice things that you can get by just looking at this three-way handshake. You obviously get the fact that it is a, you've got the Syn, but you also have some other information. You know what port we're going to. So we're going to 443, which is usually a TLS port. Usually that's the ports that people use for encryption. But to be honest, I can send any kind of data I want over any port. It's just not a default standardized port. So anytime you see this, you always go, okay, I think this is going to end up starting out or end up being TLS, which happens to be the one I'm going to be working on hopefully for next week. But that's what we're connecting to. The server's going to be listening on 443. That's what the services are listening on. We're going to connect to that. You also get this nice thing called a client port, right? The client port is there as well. And so that kind of gives us a way to identify this thing as we go through, right? Or the connection between the servers. We get the two servers, we get the source, what's connecting to or from, and what is it that it's connecting to. And then we get some really useful information around times. How fast does this three-way handshake take place? Interesting thing about this is it's really important to know that because that's the start of how you get latency timing. If my TCP three-way handshake takes place, I send the Syn up, which is the first thing, and I get a SYNAC back really quick, then usually I don't have latency. Usually. There's some other things that get involved that create latency. Oftentimes, if I have slow responses back after that, it's then server related unless it's a long transaction. But there's other things that can happen on the internet that affect that too. And we'll talk about that some as we go through some of this process. But that initial three-way handshake generally tells you that connecting to the server is pretty quick. And those are small packets, so they go pretty quick. You also can see here we get the length, how big those packets were, how much data was in those packets. And then there's some additional information that goes all the way around here, and we'll kind of talk about some of these as we go through, right? I'll get more in detail. But it's really good information for you to have. If you also look down here in the frame, you'll get some other information. You'll see the MAC address of the device. You'll see the MAC address of the device you're sending to, right? And that's always something you need to think about when you're doing packet captures, because if you don't know where the initial packet capture was taken from, i.e. you get it off a device that just stores packets, you'll want to look at that to see, because oftentimes you may have a tap or a span somewhere and it only catches it at that point, when you really want to look at it from a different point of view. Maybe it's from a firewall or from a client to a firewall, or a client to a router and that's all you've got, and you don't have anything after that router, you want to take a look at this. And so that's really important to note and pay attention to. You also get all the 802.1q stuff. So there's a virtual LAN and some other information, or your VLAN information. And I'll kind of go through some of these, and I won't have all of them in here, and I'm not going to detail out all of them. There's plenty of information on the internet about all the details around those, but I'm going to try to give you some examples of why you want to know this data and why it's nice to know this data at scale. So as you can see, we have the three-way handshake. We have the Syn, the Syn, and then we have the final act that comes back, right? So that's these three right here in the beginning. You see all that, it's really good. I've got that three-way handshake going, and I've got some information about it. So we're gonna go a little bit more in depth, and we're gonna talk about some of the reasons why I wanna know that information. So here's one of the better ones. TCP Syn received versus accepted. In other words, did I accept that connection? Did I connect up with that connection? Notice we have a drop in accepted. So we've got a bunch of sends that hit the server, but they never were accepted. There was no response back, so there's no connection ever made. Most security guys would immediately go, ooh, this is a Syn attack, right? So I've got a bunch of sends hitting the server. This is some sort of Syn attack, and the server or the firewall is not responding to those sends. And remember, you can do a Syn scan that goes to multiple ports, right? So I scan 443, 445, 446, 448. So I can have a ton of sends going to something, and that would be a pretty good Syn attack. Or send a lot of sends to the same port, right? And I might get into port exhaustion if I do it well enough, because every time I send a send to that port, is there a situation where I'm opening that port and that port's holding that connection for me for a period of time? We'll probably get into port exhaustion at a later date, but the point is that there's ways that you could open up some very serious problems by sending tons of sends to a device and ultimately overload it. But that's not always the case. This actually was taken from a server that wasn't responding. Now, a lot of people think when a server isn't responding, you're not going to see any traffic to it. That's not quite correct. Many applications don't stop sending data to a server just because it stops responding. In this case, you're still getting the sends, but you are not getting the acknowledgement back. So this server actually stopped responding at about 11:20. And this is actually one of the more valuable alerts I have off of ExtraHop. ExtraHop is a great tool. RevealX is a great tool that I use for performance management and for notifying me when things aren't working the way they're supposed to. Yes, we have SCOM in our environment, and SCOM does a great job of managing and checking in with the agent. But you have to remember about agents. Agents generally sacrifice themselves when CPU gets above a certain percentage. So they may not respond to pings, but the server may still be actively accepting connections and doing other things with those connections. Granted, it's still something I wanted to investigate, but we get a lot more false positives off of the SCOM heartbeat methods, and that's just one of the reasons why I don't trust it that much, because I get a few too many false positives. In this case, we can see that the server stopped accepting sends. It did not respond to them. Now, as long as I'm looking at bytes out on the server, we can see that nothing was coming out from the server, right? Bytes out for this entire period of time. I can see, and I'll show you the bytes out chart here in a little bit if I remember right. I hope I have it. You can see that there's no bytes out, but plenty of sends in. So there's bytes coming in and none going out. That means the server's unresponsive. It's not doing what it's supposed to be doing. Great notification to have in your environment, but be sure you're measuring on bytes out, not bytes in, because bytes in will throw you off all the time. Really cool environment, but this is, or alert. But this is why it's important to understand that three-way handshake, right? If your application is timing out, first thing I look is at DNS. Second thing I look is that three-way handshake. What's happening with TCP? What's happening with the sends received versus accepted? That is critical to look at to determine whether you've got a problem. So I'm going to dig in a little bit deeper into the IP flags. Those IP flags that are in that packet are critical. That first send, when it is sent, sets some things that are really important, and probably the most important thing that I think is the most important is this thing right here. Don't fragment. In this case, it was set. This is a big indicator that it's a browser because all browsers set the don't fragment. Some applications do, some applications don't. But don't fragment really can create some challenges for some environments, and it's related to MTU. And if you haven't had an MTU problem, that's a whole nother discussion that I'll get into here in a little while. But it is important to understand that browsers set this don't fragment bit. And this has caught me many times. I've had cases where we have really slow connections because of this don't fragment. I've seen cases where stuff on the page doesn't show up very well, or not at all, or maybe it does over time, right? It's a long period of time before it shows up. Oftentimes it's a blank page, and oftentimes the browser times out. But this is still a real important setting because it affects that connection and how do things connect. Let me show you how to test with that. So if you type in your ping, your normal ping request, ping.ip -f, and then a -l because you're setting the length of the packet. This is one of the things I get a little frustrated with people, because when they tell me, hey, I pinged whatever, I pinged this remote site, and it's showing 25 seconds of latency, so I'm not worried about it, right? First thing I ask is, did they lengthen the packet? Did they set it out to 1400 bytes? So it's a full-size packet, because when you send ping, it's sending a zero-size packet, so it really kind of moves through the buffers pretty quick. But oftentimes, if you have high latency, you'll actually start to see pings drop or latency go through the roof when you expand the length. And you do that by the L, by ping dash IP address dash L, and then the number, right? So you can see right here, I set this to 1480. And I also have the -f bit set. With the -f bit, the ping is going to tell everything that please do not fragment me. I want to go through with my full 1480 all the way through. So in this case, I'm pinging www.google.com, which tells me name resolution worked because I got an IP address back. Woohoo! That's fantastic. Can my ping get a different name resolution than NSLookup? Look it up. Make a comment. Drop me a line. Let me know. Think about that a little. So I pinged www.google.com with a -f, so the do not fragment bit set, and I put the length at 1480, and I get this thing back that says packets need to be fragmented, but DF is set. Wow, that's interesting. Notice down low, I get this www.google.com. Below this, I type in 1420, right? For the length. Hey, it lets it through. I'd love to hear some comments on this, and I'm going to go more in depth in this at a later time, but this is a little idea how that do not fragment bit is used, or why that do not fragment bit becomes important. Because this thing called PMTUD, which is Path MTU Discovery, comes set into play. It's coming soon. I'll do more of a discussion on it, but look it up. This is why the -f in a ping is important to understand. This is kind of that foundational knowledge that I'm wanting everybody to get an idea of, and I want you to kind of understand that there are multiple things to this. Most people use ping, hit the IP address or hit the name, ping, they get a response back, and they're done. That is not always going to work. That is not going to tell you latency. That is not going to tell you you have an MTU problem. Both those can affect the performance of your browser significantly. So think about that. Keep that in mind. So here's another thing, and I'm going to go through all three. When we send the TCP Syn, it sets the Syn flag. These are all the TCP flags, right? So we have a reset. Many people have already seen the resets, and some things are another, right? Acknowledgement, that's the ACK. Syn ACK. So what do you think is going to be set on the next one, on the Syn ACK? We have an urgent, it's not used very often anymore. ECN, congestion notification, congestion windows reduced, a nonce, and then we have this reserve that is not set, that is not used. We have a push notification that's set, which I don't see used very much anymore. And if you do, let me know. And then we have this cool thing called a fin, which ideally, in my dream world, every developer would close their TCP connection correctly. If they did, they would send a fin first and notify the other system saying, hey, we're done, please. But to be honest, a lot of developers don't. They leave the TCP connection open and then just let it time out. Not a good practice, right? Let it just expire, go away. Not really a good practice. In some of the older systems, the TCP timeout was 2 hours. So once that connection was made and held, it would stay there for 2 hours. Newer systems today are usually 5 minutes. Some things are less than 30 seconds, just depends. But it's really nice if they use the fin. And then a lot of times after the fin happens, you'll see several resets, both sides throwing resets out there, maybe the firewall throwing a reset. It just depends. But I have seen developers close connections just by sending a reset. So not always a good idea, but it's good to understand what all of these flags are and why they're set and the different reasons why they're set. If I had to really pick, I would pick a reset, the Syn that we're already talking about, the fin, the ack, are all the ones that I'd spend the most time trying to understand. The push, maybe. Those are ones I'd kind of dig into more, but it helps to know the majority of them and why you might see them in different reasons. So look it up, spend some time, think about it. Then we have the Syn ack. What did I talk about? What did I say would be the next one, right? We talked about the fact that it was Syn, and the next packet is called the Syn ack. So what do we have set? We have the Syn, and we have the acknowledgement set. So there's the second part of your three-way handshake. So if the Syn is your first packet, the Syn ack is your second packet, and your third packet is the client responding with an ack, what do you think will be set on the third packet? Third packet is just going to have the acknowledgement set. Pretty simple, right? Those are the TCP flags, right? When people ask that question in an interview, you know. Can you name off 5 TCP flags? Well, I can, just looking at this. There's a fin, a Syn, a reset, a push, an ack or acknowledgement, urgent, and I could do the rest if we wanted to. But now you know what those are used for, and you know that three-way handshake and why it's there, and why it's important to monitor it, because you can see things like what I just showed you earlier. So here's another tidbit that comes out of that three-way handshake. This is called Windows size, or Windows scaling, as some people refer to it. I talk about it a lot and sometimes misrepresent it, but Windows scaling is really critical to performance. And in order for you to see this, you actually have to catch the three-way handshake to really verify that it's actually working. Back in 32-bit days, you had a buffer that was 65,535, right? That's the size of the buffer that I could receive data on for that TCP connection. It's a maximum I could receive. So if I'm sending packets along and each packet takes up so much space in your buffer, right? And your application isn't pulling it out, because again, back in the 32-bit days, most time if you had a multiple processor machine, the network stack only used a single processor, and usually processor 0. And it's interesting to me, I still see 64-bit systems using the same or having the same problem, and it's partially because of this RSS thing. But what would happen is when I get to a certain stack, if the CPU hasn't pulled it out, the network stack would let me know that I couldn't send a bigger packet. I had to kind of shrink up what I was sending you. I'd slow down, basically, say, send less data. You can only send me smaller bytes, smaller packets, because I can't handle the load that you're sending me. So as that went on, and I increased, I would get to the point that it would finally send out a Windows 0, right? And so this Windows 0 packet, which people hear me talk about all the time, would then do one of two things. In some cases, it would reset and restart the entire process again. So let's say I was moving a 1 gig file from my file server. It would restart that process. And I would sit and I'd wait and I would wait. And of course, I, as the end user, never saw any difference. It just was moving it and moving it and moving it. And the timer would slow down a little bit. And the cool little bar that Microsoft has showing you stuff moving over, downloading to your machine would just slow down a little bit. But in actuality, it stopped and started over in some cases. In some cases, it just stops and pauses and waits for a little bit. And then it kicks back up and starts at a really slow. A lot of times you'll see a Windows update that will come out and say, okay, you can start sending, a different size packet, maybe a 2048, and it'll start increasing if things are catching up. So it's really important to pay attention to this kind of thing because it has a pretty big effect on performance. And I'll probably do another video on Windows scaling specifically. But the thing about this is both sides have to negotiate and agree to Windows scaling. They have to, and that takes place in the three-way handshake. And that's one of the best ways to see if I truly have receive side scaling turned on. Interesting note is VMware, most of their drivers don't turn it on by default. And last I checked, the VMXNet 3, it didn't turn it on by default. Now, in the environments that I work in, it's been turned on, and we upgrade our NICs so they get upgraded, and so it's always on. But there's multiple settings related to this around the receive side scaling. How many processors do you want it to use? And the default, I believe, is 8 on a Windows box. How big the buffers, because now you can start affecting those buffers, the send and the receive buffers. You can actually change those and increase the sizes of those. So there's many things you need to think about doing from a performance perspective based on this data. And so this three-way handshake has a lot of information. And again, you can see right here, you have your Windows size value, 64,240. Okay, but then you have this Windows scale. This right here, if you see this in both packets, both the Syn and the Synac, what this is telling you is that it's ready to do Windows scaling, and it has receive side scaling turned on. So you can send me, I have a bigger buffer available to me, right? And so that's really important to pay attention to when you see these kind of things. And you can actually look at the packets and see the Windows update coming out and telling you that it's getting smaller and smaller and smaller. And eventually you'll hit a Windows 0. Sometimes you'll see it start small and increase and get bigger and bigger and bigger. But that's one of the reasons that you need to understand this, because this oftentimes is one of the bigger bottlenecks, since by default, VMware has it turned off, or did at least. And the buffers on the NICs oftentimes are set to a default value. So even if I turn on receive side scaling, I've got it on a Windows and I've confirmed that it's on the NIC, because you actually have to go into the NIC, and I've got it on there, then oftentimes I may need to increase the buffers themselves because I'll still get Windows 0. If after you've tuned all of that and you still get Windows 0 packets, usually means that the CPU is not processing it well enough, or the application isn't pulling it out of the buffer well enough for you. And so the application may have some CPU bind problems, or you may actually have some memory problems in what's called, or better known as, private memory space. I've seen things like antivirus, some of the anti-malware, some of the advanced malware stuff. I've seen those things cause significant performance issues, and most people are only looking at the total memory used, right? And private memory is somewhat restrained or constrained, more like it. Private memory can't take up all of the memory. So if you have a private memory problem, you may have that problem and not even know it, but oftentimes you can see it because of the network stack. So it's a good thing to look at and a good thing to pay attention to. And that's just one of the things that's good for. So Why is this data valuable? I was kind of getting into that. You can tell what port we are connecting to, both the client side and the server side. You can watch reconnaissance take place if you know what you're looking for. You can get into measuring latency or latency problems, or begin to at least. You can see if the do not fragment or don't fragment is set. How does it play? Look up PMTUD. See what you find. Try pinging your network. Try pinging your network with the -L. See the difference. Try pinging the network with the -L and the -F. See what the difference is. Ask some questions. Try to see what's going on. Then you get into window sizing. Then you get into tuning the NIC buffers and the NIC buffer settings, potential application bottlenecks, and detect server performance issues just from this data that we get on the wire. So again, really valuable tool, but understanding this three-way handshake is extremely important. So here's some things where we see it at scale. Here's where we see stuff coming in. This is really cool. Really cool. RevealX has this coming in, and it shows me all the protocols that are coming in, right? And see how that's coming in right there? And yet over here, I've got no data. So this server wasn't responding. Notice some other things that are really, really interesting as far as this is concerned. See where it says TCP 389? But over here, we have, or right here, we have LDAP. Well, 389 is LDAP. Why doesn't it show it as LDAP? That's generally because the RevealX system has seen the TCP connection take place, or has seen the Syn trying to connect to 389. In this case, because you have, this is on the outside, this is actually saying it saw the Syn ACK, but it never saw the LDAP traffic to go with it. So the layer 7 traffic to go with it. So that immediately makes you think and question, did we have a connection problem? How about the SSL 443? Again, this is the same kind of thing. This shows that we actually tried to connect and maybe even started the SSL because we don't have the TCP colon 443. We have this SSL 443. So we probably started the negotiation enough for it to tell that it was going to truly be SSL, but it never finished. Because right here you have HTTPS. In that case, it fully negotiated, so it knows it made it that far. That's why knowing and understanding this whole stack becomes extremely important. You can get a lot of information out of it. It's pretty cool. And when you see it at scale, you get a lot more. So then you can take a look at things like this, the connection info, the accepted, the connected, the external accepted, external connected, closed, aborted. In this case, everything just dropped out, right? The server didn't respond. And so we can see the round trip times. And this is interesting because you've got to think about the 95th percentile. This is my worst case guys, right? Those are the ones that are at the 95th percentile. So likely 5, 10 clients, maybe. Depends on how many hundreds of clients I have hitting this. But those are my worst, right? They're at 60 milliseconds. But my 75th percentile is at 30 milliseconds. But my 25th and my 5th don't even show up. So the majority of my clients are below this 10 milliseconds, or round trip time is below that time. Second thing is this is interesting about connection setup, because this is TCP connection setup. A three-way handshake should not take long at all. But if you've got clients that are having 50 milliseconds of connection setup time, on a three-way handshake, we might want to have a discussion about that. That might be a problem, right? So you want to pay attention to that. Good stuff when you can see it at scale. RevealX does a great job with this. How about that Windows sizing, buffer issues, memory issues, host stalls, those kind of things, right? We can see that the client to this server is sending a Windows 0 in. So the server was sending too much data to it, and it goes, you got to slow down. You're killing me. Here's Windows throttles in, right? Cool thing is we don't have any out. So the server's not having a problem. It's not sending anything out. But the clients that are connecting to it are saying, dude, you are overwhelming me. And this is really common with Windows 7 and Windows 10 clients, because they really don't take advantage of RSS in most cases. Most of them are using the processor 0, if I remember right. Could be wrong on that, but last I checked, that was the case. So this server's doing really well. It's just that the clients themselves that are connecting, one, are sending the notification that, hey, you've got to change your window size. That's what a throttle is. I'm slowing that down. And two, they're sending those windows 0 in. Slow down, you filled me up. Wait, I'm too full. Hold on. So really cool stuff when you start seeing this at scale and can see this on your servers and tell it, my servers are absolutely doing great. It's just mostly the clients because I don't see any 0 windows out at all. So that's pretty cool. Nice to know my servers are set up well. They're handling the load, whatever they're doing in this case. So be sure to subscribe to know when more videos are coming. I hope you enjoyed this. Would love to hear your comments. Be sure when you subscribe, there's a little bell down there. Click the bell so you can see when new videos are uploaded. Appreciate your time. Thank you very much and have a great evening.